So in any case, I guess if you guys would just like to briefly explain what the goal was and what you did, and then show it off, that'd be pretty cool.
Okay, yeah. You want to? Okay. Yeah, so what we implemented was first, I guess, the game of Connect-4 and the AI for it. So what we've done is basically implemented the game infrastructure on the HPS and have that show up, or have that drive the VGA for our game display. And then we offloaded all of the AI computation to the FPGA. And yeah, I think beyond that, I guess the best way to see it is just to play against it. So if you want to pull that up, Andrew.
Yeah, I have it up. I can share my screen. So our user interface is just the HPS program, and we have the game being displayed on the VGA here. It's being driven by the HPS because we didn't have time to port that over to the FPGA to drive it.
Okay.
Also because the logic for that would have been somewhat complicated. But should I play, or would you like to try it?
I'll play.
I feel like we've been playing it so much that we probably know, like, when we start, if we're gonna beat it or not.
So let's see. I should be able to ask for control of your computer,
Yes.
right? Let me see here. View options. Request remote control. Okay.
Right. So basically, our HPS interface allows you to choose whether you want to go first or you want to let the AI go first. And then the screen will update in real time based on what your move does, and then the AI's move will instantly show up next as well.
Okay, so let's see. So I'll go first. So I'll type yes, and I will go in column 3.
So you're white and the AI is orange.
Okay. So I'll go in 3 again. Okay, let's go in 4. I'm not a very good Connect-4 player. So is it at this point, is it making moves with the intention, is it playing defensively, I guess?
The main driving point behind the heuristic is defensive play. Like, it prioritizes not losing over winning in most cases.
Okay.
It typically only tends to make winning moves when it detects setups that will allow it to win, either in the next turn or in the turn after.
So like in this game state right now, if I weren't to go into column 1, the AI would win.
Yes, that's right.
Yeah.
Okay. So if I go into, oh, actually, I'm going to lose either way, aren't I? Yeah. So I'll block it in 1, and then it should go in, what is that, 5?
5, yeah.
Oh, and it did.
Right. Cool.
That's really cool. So are you guys able to beat it?
At times, yes.
So the easiest way to beat it is to set up for something early and then just play until like the spot that you need to win is like the last column left, which tends to be the case in a lot of times when you have 2 people playing against Connect-4. Like the main way we programmed the heuristic for this was we approached the values and like the weights for the movement pretty much how we intuitively thought to play the game. So the first step was to just like say, looking at the next move, are there any moves that we need to make in order to either win or to prevent ourselves from losing?
Okay.
And then the next step was to say, for each column that we play, would this result in a losing configuration? And if so, don't play there.
Okay. Okay.
And
So
then
it looks.
Sorry, go ahead.
So I was just going to make sure I understand. So it first looks to see if there's any move that will that it needs to block in order to not lose, and it'll prioritize that.
Yeah.
And then it checks.
No,
to see
well,
if-
actually, first it checks if it can win on this move, because if it has a
Okay.
winning move, then it will take that, and it'll
Yeah.
show that form of aggression.
That makes sense. Okay. So first it checks if it can win, then it checks if it needs to prevent itself from losing.
Right.
And then
Right.
it looks at every possible move and considers the game states that would exist if it had played each of those possible moves.
Right. And even within like the future possible moves too, we do have some sort of prioritization scheme. So for example, in this game state that you see right here, in our algorithm, we see that the AI has the chance to set up a trap. So basically, like if it places a move here, you're forced to block, and then it can still win on the next move. So we have that heuristic programmed in with like a higher priority for that move being taken. So basically, it can set up traps if it sees that they are available.
And actually the AI that's currently programmed is like slightly more nuanced than that, in that in the first couple of moves of the game, it uses like a purely defensive, like the purely defensive AI that doesn't do any like look ahead. So it uses just our heuristic that checks, if it can win, if it needs to block, and then, what's the best position to play that defends against most number of opponent tokens. And it uses that for the first couple of moves of the game. And then as the board fills up, we switch to this other AI that has the feature of looking ahead a move and avoiding traps that are a move ahead.
Interesting. And how did you decide where the switch should take place? Was it just by playing against it?
So we found that with our current heuristic for the AI, what would happen is that if we had it running from the beginning, there were certain cases where it would prioritize, it would because the beginning of the game is relatively simplistic, but what would happen is the heuristic would sometimes misinterpret some of the starting moves. So that, for example, it would allow you to place 2 in a row side by side, but decide not to block it.
And I guess the reason behind that too is because in the initial game states with so many empty spaces, the way our heuristic works, it has a lot of columns that have equal priority at that point in time. And so in order to tie break, it would place it in like one of those. So we prioritize the middle column because that's a common strategy in Connect-4 in tie breaking scenarios. And so in those situations, if we don't account for like empty game states in the initial moves and don't play defensively, then our heuristic will misinterpret the move it wants to play.
Gotcha.
Yeah.
Interesting. Okay.
Yeah, like what? So to kind of explain that a little bit better, it's the way our current heuristic works. When we programmed this, we didn't properly take into account empty space and how that factored into score calculation. So what would happen is it wouldn't think of 2 adjacent opponent pieces as a threat, even though if they're open on either side, then if you don't block it, you will still lose. But we didn't we didn't implement the logic to detect that, just because it would kind of convolute the or not convolute, but it would overcomplicate the amount of checking that every move, that every stage of the AI checking would have to do.
Okay.
Evaluator running on the FPGA?
Sorry?
Is the move evaluator running on the FPGA?
Yeah.
Huh.
So basically the way the interface works is that the player side runs on the HPS. So basically when you input a move, it'll update the game state, and then we'll send that over via shared SRAM location. And then the FPGA will read that location and basically see that this is what the player inputted as its move. And then it'll basically generate its own move and then spit out an updated game state back to the HPS, which it can then read and update the display and then play its next move.
Is it evaluating the potential game states in parallel?
Yes. So the way we have this done is the evaluation is done in a single cycle. And we have one module that calculates whether it needs to make an immediate move. And then we have another module that basically places like an AI move in each column as kind of like a hypothesis. And then from that initial hypothesis, takes a look at what the maximum opponent profit would be for each column after making that move. And then so for all 7 of the potential AI moves, it takes the minimum of the opponent's best move as the move that it would make, under the circumstance that there weren't any moves that it had to make immediately. So it prioritizes the first module that checks if it needs to make an immediate move. And then if not, then it looks at that. And then we insert, that was our second iteration. That was our first implementation of the AI, quote unquote. And then our current implementation adds a step in between, which detects for trap configurations, meaning it places a move in each column, sees if there is a winning configuration that the opponent needs to block, and then checks after the opponent blocks if it can still win. And then if that is the case, then it prioritizes that move.
So that's the trap setting.
Yeah, so there are like 3 layers of move determination, and all 3 of those layers run in parallel.
Yeah.
So how quickly did you say this evaluation takes place, the move evaluation?
1 cycle.
Oh my God.
Wow.
It's technically not 1 cycle because we need to do 6 SRAM reads to get all of the game state information in. But the actual evaluation given the full game state takes place in 1 cycle.
Okay, so it's all combinational stuff.
Purely combinational.
Okay. It's really interesting. So as you developed this, did the AI become a harder and harder challenger for you?
Oh, definitely.
Yeah.
Okay.
Because we started off with just the purely like defensive AI that only looked at the current game state. And that is what we're using at the beginning because that's all that's really necessary at the beginning. But as you fill up the board, that becomes really easy to beat. And so we added all of these other features.
Yeah.
It's really neat.
The first iteration of the AI, which is just the one where it looks ahead 1 step, we found that to be sufficient for defensive gameplay. What we found was that the user player would tend to win because the AI wouldn't try hard, the AI wouldn't be trying hard enough to win. There were configurations where it could obviously win in 2 moves, but it just wouldn't take those because it couldn't see those,
Right.
which is why we went a step further and implemented the trap detection logic to give it a better aggression, a better just a better bit of aggression.
Wow, it was very effective. Is there any, with more time, is there any more layers of complexity that you might add to this to make it even better?
Yeah, right now the biggest issue with this is, well, there are 2 issues with it. One is that once it gets into the later stages of the game, then it finds that the AI tends to be more often in configurations where it's forced to place a move that causes it to lose. And it also doesn't detect human player traps.
I
So
see.
the next logical step for this would be to, in addition to detecting AI traps, to also check an additional step ahead and see if the human player is currently setting up for any traps.
Yeah. Right now, it's kind of like a fairly good approximation of, I guess, a human Connect-4 player, or maybe like a slightly good human Connect-4 player, because the maximum number of moves it looks ahead is 2 plus some trap detection logic that kind of simulates looking ahead further. So that is kind of, I think, what most people do when they're playing the game, but it's definitely not going to be looking ahead many moves in the future to see a situation where there's one column where both players want to avoid, and the game comes down to like who is going to fill up the board fastest to get to that column and be forced to play there. So it won't avoid situations like that. But that kind of makes it more similar to, I think, how most people would play. But if we definitely could extend the game and add another state and add more computation to look even further ahead and try to avoid situations like that.
Okay. Did you bump up against any limiting resources, or how much of the FPGA are you guys using? I guess, did you run into any like memory, like and were you pushing the limits of memory or ALMs or anything like that? Or
so I think the one thing we didn't necessarily push the limits of the ALMs, but that was the resource that we kept using more and more of as we continued in our development. I think one thing that we were getting very close to is we were pushing the limit of single cycle computation, because there were times where, you know, timing wouldn't fit in a single cycle, in which case we determined that, you know, we might have to split up that, like the 1 move look ahead and the 2 moves looks ahead would be in different cycles in order to like be able to fit it all in like the 50 megahertz clock cycle of the FPGA.
Okay.
Yeah, but then eventually with like some other like parallelization design of like what goes in parallel and what can we like combine, we were able to fit it all in one cycle.
Yeah, the original concern was if we hadn't parallelized properly, that we would not be able to fit all of the logic. Because like combinationally, the data path is pretty long. And so that was what we were trying to minimize as much as possible. Like we wanted to do as much in parallel as we could. This does not have the compilation report up here. How do I see that?
In the
Compilation report. Yeah, so we're not necessarily pushing the hardware limitations on here, but we did find that with each successive compilation, our logic utilization would kind of jump because as we implement more and more look aheads, the amount of logic required increases exponentially or multiplicatively. So like if we wanted to analyze 2 moves ahead, we'd have to first create basically 7 modules. And then within each of those modules, you'd have to check 7 moves. Right. And then if we wanted to take another further step ahead, then we need to make an additional 7 moves for each of those 49.
I see.
7 to the power.
And so it scales up, the size scales up very quickly.
Sure.
And that was also a limiting factor as to why we didn't implement Minimax, which is the standard way people would like if we were to do this in like C or Python, then there are established algorithms that can optimally play Connect-4 just by analyzing all of the different moves down like the game state tree. But we were not particularly comfortable with implementing that within hardware just due to the amount of memory that it would require.
And also those are recursive algorithms.
Also that, yeah.
Yeah, so I guess one thing to note about Minimax is, like Andrew said, it traverses the entire game state space. So what we did is we kind of made like a pseudo Minimax where we're like minimizing the opponent's maximum, right? And so we cap like how deep the state space goes in order, and so by doing that, we had to make some assumptions on like, you know, what's the player thinking at that point in time. And so that's how we were able to cap it at a certain layer in order to actually fit it all in hardware. So it's like not entirely Minimax that traverses the entire state space tree, but it is doing like a comparable calculation with like our own assumptions about how the player would play.
That makes sense. And also, I mean, I don't know what goes on in the brain of like a world-class Connect-4 player, but for me, who's not that good at Connect-4, that's approximately what I'm doing. And so it seems like it's an AI that would be good at simulating a non-world-class Connect-4 strategy, perhaps. You know, look ahead a couple moves, look out for traps, that kind of stuff.
Right.
the casual Connect-4 player.
Yeah.
Casual Connect. So this thing is so fast that if you set it up to play against itself, you could, or say have the FPGA play against the HPS or something like that. You could do an awful lot of training runs really quickly if you were trying to have it learn something.
Yeah,
That's a whole different problem, right? But
it would be able to finish a lot of games within 1 second.
something like 1 million games a second or something.
Probably like every possible game.
Yeah,
Oh,
because if it's 50 megahertz, or is it 50?
It's 50 megahertz.
Megahertz.
And then divide that by, how long is our FSM? So it's 6 times 3 for the SRAM reads plus 1, so 17. So yeah, like 2 to 3 million games per second, if that's right.
Or 2 to 3 million move evaluations per second.
Move
Move
evaluation. So then divide that by the maximum number of moves, which is
42.
42. So in the worst case, it would be able to go through 70,000.
That's a lot of experience pretty quickly.
Right. And I guess if we did like try to implement something like that where we basically train different game states, what we could do is we could probably go down even further, because we could implement like different weights to different game states in our state space tree. And so we could prune different game states in order to like traverse down the appropriate depths, which would make the computation less exponential in resources.
Right. That's awesome. It's so cool that it's such a challenging competitor, at least for someone like me.
And me. It's swamped me a couple of times already.
And Katie's won against it before.
Katie,
Well,
do you
that
want
was-
to try again?
Yeah, we're try on this AI.
Yeah, I'll play again.
Oh,
Oh, wait, did it?
yeah.
Oh, sorry.
It asked if you wanted to go first. So
Yeah, whatever.
we
that's
don't error check that.
fine.
We do error check for invalid columns or full columns though.
It's like I'm like counting the.
Is the AI white or red? I can't remember.
Red.
Red.
AI is red. Okay.
It's actually yellow and red, but in this lighting, it's
Yeah.
white.
Hmm.
Right.
You got
So I guess
blocked.
I blocked Katie's move right there.
Yeah. Block the move.
Yee.
Trap.
Nice. Yeah, so that's the step that we were talking about, is that it doesn't do a great job of detecting human player traps. As in, it doesn't detect human player traps. So this is one of the, like the faster ways to beat it is to just trap it at the beginning.
Okay.
And I guess in that game, if you noticed a couple of things. So one, it did actually block Katie's 4 in a row diagonally because it recognized that. And 2, you'll notice that since Katie had a setup in column 5 where if we play something, she would automatically win, we do not go for that move. So that's also programmed into our AI to make sure it
Okay.
doesn't self-destruct pretty much.
Really cool. Did anybody else have any other questions? Awesome. Well, thank you guys.
Thank you.